The next operation that we look at with vectors is bit part selection. Here, groups of bits can be accessed using bit part selection. For example, if we take the same declaration we had previously, this time we select a group of bits. And to do that, we specify a range, in this case from 3 down to 1 and from 6 to 4. And this is what we mean by bit part selection. So we select a part of the total group of bits. For the bit part selection from 3 to 1, we have the bit positions 3, 2 and 1. So we go from 3 down to 1, and that gives us 3 wires, these 3 wires. In a similar way with the bit part selection 6 down to 4, we have the bit positions 6, 5 and 4. And that gives us these 3 bits in data bus. So what we're doing in this case with the assign statement, we've got 3 bits which are used to drive the wire on the left hand side of the equal to, and that's the 3 wires at bit positions 1, 2 and 3. And what's important also is the order in which this happens. So bit position 4 of data bus is the least significant bit on the left hand side, and that drives the least significant wire, which is bit position 1. Then we have bit position 5 on the right hand side, drives the wire in bit position 2 and so on. So these correspond in a one-to-one manner. The convention we use when we create vectors is that we go from a high value to a low value, and we have to follow the same convention with bit part select. So the most significant expression, which is 3 here, will have to be greater than the least significant expression, which is 1. And the same with our bit part selection on the right hand side. There are 2 types of bit part selection. What we're looking at here is what's called the constant bit part. And what this means is that we use constant integer expressions for the most significant and least significant expressions. And what we mean by constant integer expressions is the values for the most significant and least significant expressions are known at compile time. And for us at this point, that means using integer constants for both of these expressions. Another aspect of bit part selection is that we can only take a continuous group of bit positions. So in our example, we've taken this group here and this group here. It's not possible to take bit positions that are not continuous. In other words, it would not be possible to take these 4 bits and this bit using bit part selection. Another way in which we can perform bit part selection is to use what's called index part selection. Just like constant part selection, this allows us to access a group of bits using 2 integers. If, for example, we have the following declaration, it's a 32-bit vector of type reg, what we can do to access groups within the data bus is to use the following. Data bus square bracket, we have an integer, instead of colon we have plus colon followed by another integer and close square bracket. This first integer is known as the base expression, and the second integer is known as the width expression. Let's take this example, data bus bracket 16 plus colon 8 close bracket. The width tells us the number of bits that we're accessing, and the base value, in this case 16, tells us the starting bit position. With our example, 16 is this bit position here. What we do with the index part select is take our base position and count out 8 bit positions starting from the base. So that brings us up as far as 23. So this group of 8 bits is accessed using the index part selection shown here. So the way it works is that the with expression specifies the number of bit positions, and base expression is the start position with the remaining bit positions in ascending order in the bit range. So with our example, the base position is 16, and we go through the bit positions in ascending order from 16. So 16, 17, 18 up to 23. The base expression is any integer expression. It does not have to be constant, whereas the with expression is constant and is a constant integer value. Because the base expression is not a constant, it can change during the simulation run. This allows the index part select to be used with for loops, which we encounter later in the course. The benefit of this feature, index bit select, is that it can make coding easier for some tasks, but it has the disadvantage that the simulation is slower when compared to constant part select, which we had on the previous slide. And the reason for this is that the base expression is evaluated during the simulation run and is not known at compile time. An example of its usefulness is shown here. Don't worry about the details of the for loop. We just want to see the basic idea, and that is that the base expression can change during the simulation run. So in this example, what we're effectively doing on each iteration of the loop, we're taking a group of 8 bits. And that's defined with the with expression here, which must be a constant. So the first group of 8 bits is this group here. The next group is this, and so on. So it provides us with a very compact way to access groups of bits. There is also a version which, instead of using the plus colon, we have the minus colon, in which the bit position selected go in descending order from the base expression.